Shadow volume. Shadow volume is another shadow rendering technique that people experimented with some time ago, but it didn't really catch on. But it is still quite an interesting technique, so we will cover it in this video. Let's look at a similar situation that we had in the previous video. So we have a camera, we have a light source, and we have some objects, some triangles in the scene. When you think about shadows, you can actually think about shadow volumes. So from each of these objects, we can extrude a volume. And this is the volume that encapsulates the shadow. Everything inside this volume would be in the shadow created by this triangle up here. When we are rendering our scene, we can look at the path that we take to render a fragment, and we can count the number of times we enter a shadow volume, and we can count the number of times we exit the shadow volume. And if we add 1 while we enter the shadow volume and subtract 1 when we exit the shadow volume, then we can see that the case where this sum is 0 is the case where we are not inside any of the volumes, thus we do not have a shadow here. But if we would have 1, then we know that we have entered a shadow volume 1 time, thus we are inside it, and we have to render this fragment as being in a shadow. So this is the basic principle between the shadow volume algorithm. So let's see how it technically works. First of all, we have a light and we have a mesh. So the first step is to find silhouette edges from the perspective of the light source. These edges kind of separate the mesh into a lit side and a shade side. So on one side of these edges we have faces that are lit by the light source, and on the other side we have faces that are in the shade. Mathematically, these are the edges where the neighboring faces have a different sign for the end.L. Those faces that are facing the light source have a positive end.L, and those faces that are facing away from the light source, they have a negative end.L. Next, we separate the mesh. So we create duplicate edges along the silhouette edges, and we break this mesh apart into 2 sections. Next, we connect those 2 sections. So we have a light gap. These are the initial faces that were facing the light source. We have a dark gap, so those are the faces that initially were facing away from the light source. And we also have this side. Now this side just connects the light gap with the dark gap. And then we project the dark gap side from these corners to infinity. So the sides will become the sides of the shadow volume, and these vertices here will be projected to infinity, forming the shadow volume. To project to infinity, you just put 0 in the 4th homogeneous coordinate of the coordinates of those vertices in the vertex shader. Remember, in the very first videos, when we talked about these homogeneous coordinates, I kind of mentioned that vectors are points located in infinity. So this is what happens here. If you put 0 in the positional coordinate of your vertex in the vertex shader, then the GPU is going to project that XYZ into infinity. And you might be thinking, okay, what is this projection to infinity? And you can imagine it this way. Let's say you have infinitely powerful laser pointer and you shoot it at the sky. Then this laser pointer is going to travel in a straight line to infinity. But from your perspective, you will still see that there is a point that the end of this light beam is always approaching. So from our viewpoint, we can see the point in infinity that this laser pointer would approach. And it's similar with this dark gap. So while we are projecting these vertices to infinity, they might still be in finite locations in our final render. But basically, yes, this will create you this shadow volume. These sides will be the sides of the shadow volume, and the light gap and dark gap kind of gap the volume from both ends. Before we continue with that algorithm, we need to talk about the stencil buffer. So previously we learned about the frame buffer, and well, you have been using the color buffer since the first practice session. So inside the frame buffer, we have a color buffer, we have a depth buffer, which you have been also using, but there is a third buffer, and this is called the stencil buffer. Now the stencil buffer allows you to mask out some parts of the scene that you don't want to render. For example, here we have these black and white values in the stencil buffer, and in the render we are only rendering these stripes that have the white values. So it's like a stencil mask for your rendering. This mask can be tested against with this stencil func or stencil testing function. And the stencil func has two main parameters. So the first one is the function. So what is the comparison function when the stencil test passes? And the value that we compare against. So we could say that when the value in the stencil buffer, let's say, is equal to the value we input here, then the stencil test passes. And in all the other cases where the values written into the stencil buffer do not equal the value that we have inputted here, then the stencil test will fail, and we don't render the fragments at those coordinates. But how do we write to the stencil buffer? Well, we render to it. And when we're rendering, we can define this GL stencil op. And this configures how do the values in the stencil buffer change depending on if the object we're rendering right now either passes or fails the stencil or depth tests. And there are three cases it checks and uses to write to the stencil buffer. First of all, we have this S-fail. So this triggers only when the stencil test itself fails. So usually we would have already something in the stencil buffer. The depth test doesn't matter here, but now in the new render, when the stencil test fails, then we can choose what do we want to do with the values at that coordinate in the stencil buffer. Do we want to zero them? Do we want to replace them with something, decrease them with something, increase them with something, or keep them? Or there are other options here as well. The second case that is tested is when the stencil test passes and the depth test fails. So in the cases where the depth test fails and stencil test passes, we can do another operation on the values in the stencil buffer. And the last case is when both the stencil test and depth test pass. If both of those tests pass, then we can configure a third operation to be performed on the values at those coordinates in the stencil buffer. So how do we write in the stencil buffer with shadow volumes? First, we render the back faces of the shadow volumes and we decrease the stencil value only when the scene depth for those back faces has passed. So those back faces of the shadow volumes themselves don't write to the depth buffer, but they use the depth buffer already set by the scene geometry, and when the depth test passes and we happen to see a back face of the shadow volume, then we increase the stencil value by 1. The back faces of the shadow volumes where the scene depth test would fail, well, that would be behind the scene geometry, which we wouldn't see anyway because then we're rendering the scene geometry itself already. So only those are relevant that pass the scene depth, and currently we're rendering the back faces, and for those coordinates we decrease the stencil value by 1. Next we render the front faces that also pass the scene depth testing, and in those cases we increase the stencil value by 1. And this creates us this situation like we had before, that when we enter a volume, the counter is increased by 1, and when we exit the volume, the counter is decreased by 1. So now, when the stencil value is 0, then we render direct lighting onto the scene geometry. And here are some more different cases. So here is the case where we enter a volume, we increase the stencil buffer value by 1, here it's not 0, we are in the shadow. Or over here we enter a volume, we increase it by 1, but we also exit the volume, so we decrease it by 1. So if there would be scene geometry here, that would be illuminated, but next we enter another volume, so we increase the stencil value by 1 again. So thus this fragment would be in the shadow. Now you might have noticed that this case, the second case here, has a problem. When the camera itself is in the shadow volume, then we are not entering or exiting the volume on the path from the camera to the fragment. Thus we don't know that this should be in the shadow because the stencil value is 0 and we are rendering this with direct illumination. So this is a problematic case for this particular technique. But there is a solution. So right now, note that we configured the shadow volumes to change the stencil buffer only when the depth testing passed for those volumes. The solution for this particular case is actually to use the faces of the shadow volumes when the depth testing fails. And this is also called Carmack's reverse because John Carmack used it in Doom 3. Now, what did he do was he counted the volumes that are behind the current fragment. This is where the depth test fails, because when the depth test fails, this means that there is scene geometry in front of that part of the shadow volume. So we are not actually counting anything that is between the camera and the fragment, rather we are counting all the back and front faces of shadow volumes that are behind the rendered fragment. So in the first case we see that there is this side of the shadow volume behind the fragment, we are exiting it, we are subtracting 1. So this means that in our space, this fragment has an exit from the shadow volume from its current position, meaning that it has to be inside the shadow volume. This approach fixes our problematic case from before, so when both the camera and the object are inside the volume, there is still an exit from the volume behind our object. Or over here, we could exit the volume once, enter another volume, exit another volume, we would still have this -1 counting this one exit. If our object would be in the middle here, then we would just have one entry and one exit of another shadow volume behind the object, meaning that this object would be illuminated. And this is the result you would get with the shadow volume algorithm. So you have these spheres again, and you can see that there are these shadows, and these are the actual volumes that are extruded to infinity from the scene geometry. Now the shadow volume algorithm was used in Doom 3 to create these very crisp and sharp shadows. So here you can see that there are these sharp edges on these shadows, and well, these are sharp because they're extruded from the scene geometry itself. They're not stored in some texture like shadow mapping, and well, in this Doom 3 horror game, they actually wanted these crisp looking shadows because they look more menacing. So from this video, you should understand the shadow volume algorithm, how those volumes are created. So we have the silhouette edges, light gap, dark gap, and we extrude the dark gap to infinity and create a side between the light and dark gaps. You should also understand how shadows are tested through stencil testing, and what's the difference between this deft pass and deft fail approaches. How does the deft pass approach create this problematic case where the camera is also inside the volume, and how this deft fail, also known as Karmak's reverse, solves that issue. You know that the shadow volumes were used in Doom 3. In addition, you also learned the stencil buffer. This is the third specific buffer in the frame buffer. You learned about stencil testing technique and its parameters, and the stencil creation technique and its parameters.